base start pointing. Only if it's E2 you got to worry about it. This is done with a little bit of water added too. Anyway, if you lose this OH and this H, you get this product. And if you lose this OH and one of these two H's, you get this product. And you got both. Because remember when you did the gas chromatograph, those you did, some of you may not have, you got 2 weeks. So, which is the major product? The one on the left or the one on the right? Which is the more highly substituted alkene? You might have to draw in the hydrogens. Remember, carbon atoms have a total of 4 bonds. So this alkene has on this carbon 1 R group, and on this carbon 2 R groups. Or it is 1 hydrogen. This alkene has on this carbon 1 R group, and on this carbon another R group, it is 2 hydrogens. So the more R groups you have, the more stable it is. Or the less hydrogens you have attached to one carbon, the more stable it is. So this has 2 hydrogens instead of 1. So the major product of the reaction you did in the lab was this. This was that one located in this position. Although you do get some of the other. It's about 15 or 16% of this, and about 84 to 85% of this. Okay, so just remember, sometimes you have a choice as to where double one goes. Be able to predict which the major product will be. Okay, now there's tricks chemists have to try to force substitution or elimination to take place. So let me just give you one example. The best thing to do is probably just memorize this table here. There's so many little details to keep straight. But basically, if you have something like this, anytime you add sometimes a lone pair, this lone pair acts as a nucleophile. If it acts as a nucleophile, you're going to get substitution. If it's a lone pair that acts as a base, it attacks the carbon as a nucleophile, it attacks a hydrogen, and it's called a base, and you get elimination. So substitution, elimination, they always compete with each other. Can you make one more prevalent over the other? And the answer is yes. If you have a big, giant, bulky compound that has a lone pair, it's really hard to get in here. So if you don't want substitution, if you want elimination, make your base huge. And the base that we usually use is this. This is huge. And it's not going to be able to get in and attack this carbon. That's enough. It's just too much steric constraint. But it can hang out on the fringe. It can hang out on the fringe and pluck off this hydrogen CSO10. If you want elimination to take place, use a big, giant, bulky base, and it won't be able to get into the carbon. It's just too crowded to get in there and attack this carbon. Instead, it hangs out on the fringes and plucks off a hydrogen. So this big, bulky base will tend to give you elimination carbon. On the other hand, if you want to get rid of this halogen, if you want to substitute for something else, then use a small base, like the methoxide ion. This is a small base. And this can get into the carbon and kick out the halogen. See? So that's one trick that they'll use sometimes. The size of the nucleus, the size of the substance has a lone pair. See, both, let's call it T-butoxide ion, and the top one is the methoxide ion. Both of those have a negative charge on oxygen. They both have the potential to be a nucleophile or a base, but the bigger the material is, the bulkier it is, the harder it is for it to be a nucleophile. It's easier for it to be a base. And the smaller ones tend to be able to act as
nucleophiles and attack carbons. So chemists have ways to try to force feed a reaction, but it doesn't always work out. You always have to worry about getting a mixture when you do a reaction, substitution, and elimination. So I will tell you this next test if I'm looking for the substitution product or the elimination product. Now, there's a little cheat sheet for you. There's, you gotta take this with a grain of salt. But here's a good cheat sheet that I might even provide you if you remind me because it's not memorized. It just tells you which groups tend to be nucleophiles and which groups tend to be bases. Okay? And I know what's in there. Gotta get to the correct chapter. So it's kind of a useful cheat sheet to have. Some things only act as nucleophiles. This is on page 375. So take this to the bank. The guys on the far left, they never act as bases. They just don't. They're too weak to act as base. They can act as nucleophiles. Okay, so any halogen, if it's a halogen that's negatively charged, it's not going to act as a base. You're not going to make HCl or HF or HBr. You're not going to make those. This is not going to pull off a hydrogen from an organic molecule. And if it's a sulfur that has a lone pair, it's going to be nucleophiles. So these guys, if you see these guys reacting, it's only going to be a substitution reaction. They're not going to act as a base. Okay, so I'll give you that information for reminding you. Okay. Then you have the guys that can only be a base. And don't worry about this for now. We'll get about this later. These are fancy compounds. I've never seen them before. This author must like these. But usually hydride ion, usually sodium hydride. This can only act as a base. This doesn't act as a nucleophile. But don't worry about that. So these guys can be nucleophiles only. They don't have a split personality. They're kind of boring, okay? But these guys are the exciting guys in that if you've got an oxygen with a lone pair, it can be either a base or a nucleophile, okay? So that's where the excitement comes in. I'm going to have to tell you that we have methoxide ion, and I'll say it's acting as a nucleophile or it's acting as a base, okay? Because they have split personalities. So if you have an oxygen as a nucleophile, it can be either a nucleophile, if you have the lone pair on the oxygen, it can be a nucleophile or a base. If the oxygen is negatively charged, it will be a strong nucleophile or a strong base. If the oxygen is neutral, the molecule is neutral, it's going to be a weak nucleophile or a weak base. So oxygens are like, Dr. Jekyll and Mr. Hyde. There's no telling what the heck they're going to do. Sometimes nucleophiles, sometimes bases. But again, if it's negatively charged oxygen, it's going to be strong. Okay? And this tends to go by the SN2 and E2 mechanism. Anyway, so that's something you want to just like before, we talked about SN1 and SN2, strong nucleophiles tend to go by the SN2 mechanism. So strong nucleophile mean SN2 mechanism operating, strong base E2 mechanism. If it's a weak nucleophile, then it's the SN1 mechanism operating in the weak base, E1. So kind of trying to keep that in mind. I'll provide you with that. I probably won't give you this kind of information here. I'll do it strong. And then these guys act as nucleophiles only, okay? These tend to be strong nucleophiles because they're charged. They tend to go by the SN2 mechanism, and this tends to be a weak nucleophile. These guys, they tend to go by the SN1. Okay, so if you see a reaction with these guys, substitution is taking place. If we see a reaction with these guys, who knows? It could be substitution or elimination. Now, the book tries, in an attempt, a confusing attempt to try to have you make predictions, forget about it. It's just nuts trying to figure this out. They have possible outcomes. If you have, but don't bother memorizing this. It's just going to be too crazy. And they have more possible outcomes at the bottom here. It's just, it's just not that useful. And they have more possible outcomes on the next page. So, you go nuts trying to just, understand all these possible outcomes. What happens if this. So I would just say, what you can do though, you should do, is understand this. It kind of summarizes it a little bit better, a little bit more succinctly. That what you see to the left, these guys act as nucleophiles. You get SN2 for the negative charge ones, you get SN1 for the neutral ones. These guys, they're all going to map. If it's an oxygen as a lone pair, it would be nucleophile or a base. Take your pick. If it's negative charge, it's a strong nucleophile or strong base. If it's neutral, it's a weak nucleophile or weak base. So try to remember that, and that will set you free. Don't worry about those other possibilities. There's just too many. What I used to call it, concept mapping, I think. He likes concept mapping, but it's gone amok in this okay. Now, I'm going to ask you, just like I did on this test, I'm going to ask you which reacts fastest by an SN1 or SN2 or E1 and 2. So beat that to death. And I think might be good to know this. I think that covers all the high points. So page 378, 379, what is concept map? Don't worry. Unless you want to drive yourself insane. Now, one thing to remember is that the methyl halides, when you have one carbon, you can't have elimination. So I'm not even going to say I'm looking for the elimination product or I'm looking for the substitution product, because if you only have one carbon and you have an OH or a halogen, the only thing that can happen is substitution. Some nucleophile can substitute. You can't get elimination. You can only get elimination if you have two carbons with a halogen or two carbons. Then you can potentially get elimination or you can get substitution. Okay, so that's when you got to start worrying. Okay, and so we won't worry about this. We're talking about elimination. So you have this is a first degree, right? It's got the carbon has a halogen, has one uncarbon attached to it. This is the first degree alcohol. A second degree alkyl halide will look like this. A second degree alcohol will be this. And then the third degree alkyl halide, carbon has a halogen, has three electrons attached to it. And this is the third degree alcohol. Okay, so first, make sure you understand that. And then let me give you a trend, and then a bunch of hand-waving arguments to try to convince you why this is so. Okay. So what is the reactivity? It's SN1. You've learned that SN1 mechanism, third degree alcohols, third degree alkyl halides react the fastest, followed by second degree, followed by primary. They react the slowest. And that's because the SN1 mechanism, remember, involves formation of a carbocation. And if you form a third degree carbocation, would be formed, start with a third degree alcohol or a third degree alkyl halide, you could have formed a third degree carbocation. And that's stable, see? Whereas a first degree